Thank you everyone for coming at this non-standard time for the SNAPP seminar. We appreciate the fact that you were able to make it. It's our pleasure to have Max Raginsky today. He's done an an extremely large body of work in many different areas, spanning stochastic control, applied probability, information theory, machine learning. And today he's going to be telling us about a variational approach to sampling in diffusion processes. Max, over to you.
Well, thank you, Ashwin, for the introduction. Before I start, I have a small request. My eyesight is not great, so if somebody uses chat to ask a question, I just won't. I might not notice it. So if you want to ask a question, just feel free um, to just speak up. Or if you raise your hand, I know the raised hand on Zoom is finding that as an exercise in target tracking, which I don't really have the best capabilities for. So
I'll,
I'd
I'll let
really,
you I'll let you know if there is such a question, Max.
awesome. Thank you. All right. So this will be a talk on a variational approach to sampling in diffusion processes. I'll make everything precise. Some of you may have heard me give shorter version of this talk at the conference on decision and control in Milan um, in December 2024. This is a full version, and it's dedicated to the memory of really one of my sort of main inspirations in terms of style of approaching research problems, in terms of kind of outlook on the interaction between mathematics, engineering, and life, and just the overall questions of scientific, literary, and philosophical taste. Sanjoy Mitter, who passed away in the summer of 2023. And actually, this paper will appear in a special issue of Communications in Optimization Theory, dedicated to the memory of Sanjoy. So it's a bittersweet kind of a pleasure to present this dedication. And Another reason why this dedication to Sanjoy is meaningful is that the talk will kind of build on a paper that he wrote in 1990. Was it 1998? I don't remember the exact year of that paper. With Nigel Newton, where they proposed kind of a variational formulation of the Bayes rule. Um, they were not the first ones to do it. I mean, it has been sort of done independently in several fields, in economics and statistics and others. The distinctive aspect of this work of Mitter and Newton is that they then um, used it to develop a control interpretation of path estimation problems involving diffusion processes. So basically, the idea there is that you phrase the problem of constructing a posterior density um, for an unobserved diffusion process given an observed noisy version as as solving a problem in stochastic control. So the starting point really is this Gibbs variational principle, which pertains to minimizing certain functional and space of probability measures, the free energy. So the idea there is that we have uh, a space of probability measures on some set, and we fix a reference probability measure p, and then we define a free energy functional, which takes any other probability measure p tilde and computes a sum of two terms. We have an expected energy, so h is some observable or a function that we're interested in, call it energy, in analogy with statistical physics. And then we add to that the relative entropy between p tilde and the fixed reference measure p. So you see, you write it as a sum of an expectation of h and the relative entropy. Um, and then if we're interested in minimizing this free energy over all choices of tilde p, then under appropriate regularity assumptions, we not only have an exact expression for the minimum value of the free energy, which actually involves only the reference measure p and its exponential and the exponential moments of minus h under that, but in fact we know that the minimizing probability measure is unique and takes the form of this Gibbs measure, right? So we tilt P by the exponential of negative h. Now we renormalize, and this measure is the unique minimizer of the free energy. So it achieves the optimal trade-off between expected energy and entropy. And the Gibbs designation really comes from statistical physics, where probability densities of this form correspond to equilibrium states of physical systems. Right, so in statistical physics, this is related to something called thermodynamic stability, where the idea is that over a long time, physical systems tend to relax to such Gibbs measures. So at a fixed temperature with h given by the Hamiltonian function of the system, we'll observe the process of relaxation towards equilibrium. And this equilibrium is postulated to be either the local or the global minimum of the free energy. And it turns out that Bayesian inference, where you transform a prior probability measure on some space into a posterior one, conditioned on some evidence, can be phrased in this way. So this was precisely the work of Mitter and Newton, which I guess was 2003, not 1998, as I originally said. But again, this has been discovered independently in several settings. Probably one of the first papers was by Zellner, who was an economist. His early derivation was very complicated, used the calculus of variations, and then he published a short note saying that one of the colleagues in the economics department, I think at the University of Chicago, told him that this is just a simple consequence of the fact that the relative entropy is non-negative. And in statistics, for example, Walker had similar ideas in a different context. But the main thing is that we can think about the process of passing from the prior P to the posterior, let's say this P star of X given the evidence Y, as minimizing a free energy where the energy functional H is essentially the negative log likelihood of X given the negative log likelihood of seeing this evidence given the hidden X, and then the relative entropy is between the posterior and the prior. So I want to stay to the prior, stay close to the prior while minimizing the negative log likelihood, right? Okay, and so really the task of sampling from this Gibbs distribution from P star is complicated. In discrete settings, the complexity arises from the fact that we have a normalization factor, this partition function, right? This integral in a denominator. And so if we want to sample from this posterior distribution, then we have to possibly come up with a scheme that sidesteps this issue. And as I will get to in a moment, when the reference measure is a diffusion is a probability law of a diffusion process, and the Hamiltonian function h is of a particular form that kind of looks like a control cost, then the problem of sampling from P star can actually be written as the solution of an optimal control problem, where the idea will be to add a drift to the reference process that does not require computing this partition function. But before I do that, I want to also talk a little bit about constrained marginals, because that will come up in the rest of the talk. So suppose that our space actually has a product structure. So we have some x and z, and here the idea is that x is some variable with a probability distribution mu, and then conditioned on x, we draw some other random object z, and so both the reference measure and the candidate minimizers for the free energy will have that product structure, right? We just disintegrate them, and suppose that we impose a marginal constraint on mu tilde, right? So mu tilde is the marginal of this. On here, I guess I should have, I think this p tilde right here should be mu tilde, Right. We have a let's say a constraint set for the marginal on X, and we still want to minimize free energy subject to this constraint. So in that case, we use the chain rule to decompose the relative entropy into two terms. The first term accounts for just the marginals on X, and the second term is the conditional entropy that accounts for the conditionals of Z given X. And then the free energy splits in the same way, right? We can write it as a sum of the relative entropy just on X marginals. And then we have the average of free energies conditioned on X. And then we can solve, the idea is that we can solve the free energy minimization for each X. And then the minimum of free energy, again, will be written as the minimum of another free energy like functional, where now the what we're doing is we are still minimizing over the constraint set, this mu tilde, the relative entropy to the marginal mu plus the energy, but this energy is actually the solution of the free energy minimization problem conditioned on X. Again, I'm giving this ahead of time, kind of front loading the presentation with this because this will come up later when we have to consider various marginal constraints when we deal with diffusion processes. Okay, so when we talk about sampling and diffusion processes, this was, I think, the kind of a real conceptual contribution of that paper by Mitter and Newton. And the idea is the following. Suppose that P is actually the probability law of a path, right? A path of a diffusion process on a finite time interval from 0 to capital T. And we're given the initial condition that has some marginal distribution mu. We could consider a special case where this marginal is just a Dirac delta sitting at a particular point, and we have drift and diffusion coefficients that are given to us. We have a Brownian motion, and we impose enough regularity conditions for this stochastic differential equation to have a unique strong solution. And our goal is to obtain samples from the Gibbs measure. So here, the reference measure, P, is the probability law of this diffusion process with initial condition mu, drift B, and diffusion coefficients sigma. And then we're given a Hamiltonian function, h, which is a function of the entire path. And it consists of two parts. It consists of kind of a running cost, integrated from 0 to capital T, given by this state and time-dependent function f. And we have g, which is the terminal cost, right? So we might want to sample either from this Gibbs measure, or we want to sample from the one where the reference process is just a conditional law of P given X. That's when we have the initial deterministic condition. Right? So the idea here is that we can actually accomplish this by adding the drift to the reference process. So in other words, sampling from this Gibbs measure is actually a problem of optimal control. And as we'll see later, we'll be able to have an exact form for the optimal control in terms of the solution of a certain PDE. It's going to be a second order PDE, since we're dealing with diffusion processes. And this PDE will actually be a Hamilton-Jacobi-Bellman equation for an optimal control problem. Okay, so here's the idea. We introduced the controlled equation, which amounts to adding a drift to the reference drift. And following the idea of Mitter and Newton, we're going to parameterize that drift in a particular way. We're going to multiply it by the diffusion matrix, which is sigma sigma transpose, for a very simple reason. We want to make sure that we can apply the Gersonov change of measure here, and pre-multiplying the control U by sigma sigma transpose actually allows us to work with a situation where A is not necessarily positive definite, which can actually cover interesting cases of relevance in applications. So here, U is going to be a process, which is a control. We're going for weak solutions. right? So the approach of Benish from 1971 to these optimal control problems in the space of measures does rely on the notion of weak solutions. So here the idea is that since our goal is sampling, we care about attaining a particular probability law. We are free to define everything on our custom probability space instead of aiming for strong solutions where the probability space is given to you, have a Brownian motion defined on it, and everything has to be measurable with respect to that. Here we're allowed to construct our own probability space that'll give us the right stochastic behavior in terms of achievable laws. And here the idea is that we would like to characterize admissible controls are the ones that give you a valid Gersonov change of measure. So in other words, we define this exponential martingale mu, which is parameterized by the controls. And here, as you can see, this is precisely where we can actually accomplish this change of drift when we multiply the control in the above equation by sigma sigma transpose. So this exponential martingale, indeed a true martingale when the expected value of mu is 1. Right, this is just by necessary and sufficient conditions for the Gersonov change of measure. And then the idea is to find an admissible control. So of the space of such controls that are admissible in the above sense of Benish, we need to find one, U star, such that when we use it, the corresponding Gersonov change of measure, mu star, this exponential martingale, actually gives you the desired Gibbs. Right, so in other words, the Gibbs density, this with respect to the reference, can be attained using U star as the control. Right, that's the formulation. Okay, so here's the main idea. I'm going to outline it heuristically. The rigorous proof uses ideas from the theory of stochastic flows, and then you have to first consider a special case where everything is bounded and sufficiently well behaved so you can actually implement the strategy exactly, and then there's a mollification argument at the end that allows you to do this more generally. But the basic idea is as follows. We're going to try a gradient ansatz for this optimal control. So U star is going to be in the form of the negative gradient of some function v. The gradient here is with respect to the space variable. V will depend on both x and t. So the idea is if we ask for the control to be of this gradient form, what should this v be? And so let's try a particular v smooth enough so we can actually apply the Ito's lemma. So we're going to apply Ito's lemma to the reference process. And when we do that, we end up with an equation for v of xt along the trajectory of the reference process for a fixed deterministic initial condition. So using Ito's lemma, we end up with these the usual terms, and then the idea is to eliminate the stochastic integral, right? The Ito integral of sigma transpose grad v. We express that in terms of the other remaining terms in that identity, and we substitute that into the Gersonov density, right? If U star is of this form, we substitute that into the Gersonov density, for which we have the expression mandated by Gersonov's theorem on the left, right? And on the right, we want to choose v in such a way that we have an equality for all realizations of x, right? And so this will hold if v solves this partial differential equation, which actually is a particular form of the Hamilton-Jacobi-Bellman equation for an optimal control problem. So we impose the terminal condition. At time capital T, our v should be the terminal cost. And then L is the generator of the reference process, F is the running cost, and then this half squared norm of sigma transpose delta V is precisely what arises from Ito's lemma. So here the idea is that we express the stochastic integral in the exponential martingale using the other terms in the ethos lemma identity, and then we just pattern match against the desired form, right? And then we can, of course, use the Feynman-Kautz formula to analyze rho, which is given by exponentiating negative v, that even though the equation for v is nonlinear, this is a well-known setting, popularized in the context of control by Wendell Fleming, who I think was the first one to introduce this. But in the theory of PDEs, this is known as the Cole-Hopf transformation. So when we go to rho instead of v, rho obeys a linear PDE, which we can solve using the Feynman-Kautz formula, and so we end up with an exact expression for the optimal control as the negative gradient of this v. And of course, it does end up looking like the since this is a cost to go, this will be a free energy, minimum free energy for a particular problem at the intermediate time and the intermediate state. Okay, so this is the basic idea. And as far as I know, this trick of matching the Girsanov density against the desired measure first was proposed in a paper, I think 1976. That one I remember, a paper by Ezawa, Clowder, and Shep, in the context of basically obtaining biased samples of killed Brownian motion for problems in physics. They wanted to avoid this, very expensive killing process where you sample multiple paths of the Brownian motion, and then you consider killing these trajectories at a certain rate, and then that's kind of a rejection sampling to obtain to estimate a particular Feynman-Kautz average. Instead, they said, why don't we add a drift to the Brownian motion to give us a sample of what we want? And this is what you end up with. Okay. So I'll just list briefly the technical assumptions on this. So first of all, the reference diffusion process, right? It has the initial distribution as B and in sigma. We assume that both B and sigma are Lipschitz in X, uniformly in time. We assume the usual growth assumptions that B grows at most linearly in X, sigma is bounded. And then these assumptions ensure that the reference SDE actually has a unique strong solution. The Hamiltonian, consisting of the running cost integrated over time and the terminal cost, both F and G are bounded from below. We assume that they have to be continuously differentiable and have enough growth, controlled growth in themselves and in their first derivatives. And we assume that their first derivatives are Lipschitz continuous. These are probably not the minimal conditions that you can impose, but they're enough to comfortably accomplish the above proof in a fully rigorous way. Right? So here the idea is that we want enough conditions in order to apply the Gibbs variational principle. So with these assumptions, this is the main theorem, and then I'm going to in the rest of the talk, I'm going to instantiate it in various settings. Okay, so under the above assumptions, the control U star given by the negative gradient with respect to x of v, and v has a specific form. So here we're considering the reference process x with a given initial condition little x starting at time t. So this is a cost to go, so we start at time lowercase t. And we assume that our process is in state x at time lowercase t, and then we consider the rest of the times all the way up to capital T. And so this control is admissible, meaning that it does give you the full-fledged Girsanov density, and it satisfies the following. First of all, it minimizes the expected cost with a deterministic initial condition x over all admissible controls. The density mu star is the desired Gibbs measure, so that this exponential change of measure gives you what we want with the deterministic initial condition. And it attains the minimum of the free energy. Once again, here the reference measure is conditioned on a given deterministic starting point. And so the proof really is more or less exactly the same as in the Mitter and Newton paper. Although I have streamlined it in a few places. They were working with the filtering problem. but it really can be made more general. So the idea is that first use the theory of stochastic flows. We'll want to characterize the dependence of the solution on the initial condition and on the starting time, so we can actually perform some differentiation of expected values with respect to this. So the idea is that this candidate control U star, which we postulate, has a stochastic representation as essentially log derivative of a function rho, where rho is the solution of Varro has this expression here, and again, previously I motivated it by the Feynman-Kautz theorem, but of course, in order to argue that this rho solves a certain PDE, we have to make sure that the regularity assumptions of Feynman-Kautz are satisfied. They won't always hold. So the interpretation of this as solving the Hamilton-Jacobi-Bellman PDE has to be interpreted appropriately. But the point is that we're starting slightly sort of in a slightly reversed engineer manner. We know what the optimal control should look like, and we want to argue that that this is indeed optimal, right? So in a special case where B, the drift, and the cost functionals are bounded, and if the diffusion is uniformly elliptic, so this A, which is sigma sigma transpose, is positive definite, and the minimum eigenvalue is bounded away from zero uniformly in X and T, then actually the above procedure, the heuristic idea, works exactly. So it'd be fully rigorously justified. And then we use essentially a regularization process where we mollify B, F, sigma, and G, and then show that the approximation preserves all the properties we want, in particular this representation for U star, and then arrive at the desired claims at the end. That's the main idea. But really, the core is this item 2, where the heuristic argument that I outlined earlier is rigorous. Okay, so now that we have this theorem, let's see what it can give us. So the first example is what I alluded to, this paper of Izawa, Clowder, and Shep about Feynman-Kautz averages. It's 1974, actually, for some reason. I really should stop, quoting years. My memory for those is not as good as it used to be. 1974. So Izawa and Clowder were physicists. Larry Shep, of course, was a probabilist. And they wanted to solve the following problem. So suppose you have some sort of a potential V, and you want to obtain samples from this kind of a biased Brownian motion. You start a Brownian motion at point X, and then you want to tilt it using V towards paths that have smaller value of V. Right, and so lambda is this killing rate, and the idea is that previously you would use this idea that you sample a Brownian path, and then each time it can get killed with probability that's governed by lambda v, and then you have to do this many times over, and then you average over the paths that survive, and you get this sample using Monte Carlo. So Izawa, Clowder, and Shep wanted to avoid this. Instead, they proposed a control-like procedure for sampling, which is precisely the idea that the method based on killing is like importance sampling. You reweight the samples from P, but you could also transform the paths generated by P using some sort of transformation, right? And so it's basically kind of changing the order of processing. In killing or in importance sampling, you first sample from P and then you process those paths. Whereas in this control interpretation, you actually change the distribution of X. And so in that setting, the drift is zero. The sigma diffusion matrix is the identity because the reference process is a Brownian motion starting at X. F is lambda V, right? That's our running cost, and the terminal cost is zero. And then to obtain a sample from this killed Brownian motion, you use the following stochastic differential equation. So you take a Brownian motion starting at X, you add drift to it, and the drift is U star, and U star is the negative gradient of V, and V is given in terms of the negative log of this expected exponential. And in fact, you end up with the PDE for V, which is our Clowder and Shep derived. And this is actually a very simple instance of an optimal control problem, right? Where your cost is actually one half of the squared norm of the drift plus the running cost, right? That I think I had that in the theorem. It's right here, right? So your cost has two contributions. You have the original f from your Hamiltonian, and then you have the squared norm of the control that you add, right? So that's what you end up with. And as far as I could tell, the authors of this paper were not aware that this is actually they're solving an optimal control problem. Okay. The next example that I would like to discuss is the time reversal of diffusions, which is an interesting problem in its own right. Right? If I have a diffusion process and I over a finite time interval, and I reverse it in time, when is the reversed process itself a diffusion process? Which means that in particular, it has to be a continuous time Markov process. It has to have continuous sample paths. It has to have the strong Markov property that has to do with the behavior and their stopping times, and it has to solve a martingale problem in this Stroke-Varadon sense. So satisfying all of these assumptions for the reverse process is non-trivial, right? So the question is, when can we guarantee that time reversing a diffusion process gives us another diffusion process? It's also interesting from kind of this conceptual physics point of view, because diffusion processes represent irreversible behavior, right? So thermodynamic behavior, which is inherently irreversible, has kind of an arrow of time aspect to it. If we reverse the time, will it still look like a diffusion process, right? So somehow this irreversibility is preserved in both directions. So one of the first papers was by Brian Anderson in early 80s, and then Hausman and Pardue a few years later gave probably the most easily verifiable regularity conditions for this to hold. But the solution looks like this. Here's our original diffusion process with drift B and diffusion coefficient sigma, and then what we do is the following. We want to define the time reversed process. So this x bar t is the time reversed version of x on a finite time interval. So x bar 0 is going to be x capital T, etc. So this runs backwards in time. And the idea is that this will be a diffusion process with explicitly characterized drift B bar, explicitly characterized diffusion matrix sigma bar, and explicitly characterized Brownian motion W bar. So this Brownian motion is actually explicitly constructed through a particular change of measure argument. And the results of Anderson and Hausman and Pardue tell us that the time reverse drift B bar consists of two components. The first is the what you would expect if there were no diffusion terms. You run the time backwards, so your drift is going to come in with a negative sign and with reversal in time. But then the second term that's added to it involves the density of the forward process. And for that, of course, you need to ensure enough conditions of regularity for this density to exist and to be differentiable. But so it involves a density. It involves the derivatives of this density multiplied by the volatility matrix A of the original process. The variance, the diffusion matrix, is simply just the time reversed variance of the original process. And so here P, lowercase pxt, is the density of the original process running forward in time. And again, you impose minimal conditions for this density to exist. In the special case when sigma only depends on t, the drift of the reverse process has has the same form. It has the kind of classical drift reversal, right? Negative b evaluated at the time of capital T minus little t, and then it has sigma squared t, right? We assume here that if the drift is if the diffusion part is independent of space, then we have sigma squared times the gradient of the logarithm of the time reverse density. So in statistics, this is called the score. It comes up in Taylor expansions of densities around the parameter. So, in the context of machine learning today, this is actually a main object in something called the generative diffusion models, where the idea is that once you learn the score from data, because you don't know this underlying density, once you learn the score from data, you can essentially accomplish sampling from a desired probability measure by running this process in reverse. So the forward process degrades your target density by adding noise to it, and then you can reverse it by sampling noise, some sort of an unstructured prior, and then adding the score term to it in order to steer the system towards the desired density. So it turns out actually that we can think about this extra term in the time reversal literature as an optimal control. But of course, then we have to first introduce an appropriate reference process. The reference process will actually uh, have the following form. So we're going to first write the drift B bar from the previous slide using the product rule for differentiation. We're going to isolate the term. Essentially, what we want is to have a term like this. We want to show that the gradient of the log density is the optimal control. So for that, we simply isolate, just rewrite this expression and group together the terms that consist of negative b plus whatever is left over from essentially applying the product rule. So that way, when I differentiate this product, I end up with something that looks like this and something that still has the contribution of the um, divergence of the divergence in the vector calculus sense of the diffusion matrix, right? And so that's going to be our reference process. So the reference process is going to have a drift that's going to have the kind of the classical drift term plus an additional term that depends on the divergence of A. And here the main thing is that if we differentiate A, then this P, which comes in a denominator, will cancel with this P, so we're left with a term that only depends on A, does not depend on the density. That's the key point. So that's going to be our reference process. So this is already a process that's partly reversed. We just don't have the right control term that accomplishes the full reversal. And so the target Gibbs measure actually will be a mixture of Gibbs measures. So for each starting condition Z, we're going to run the time reversed process, and then the Hamiltonian functional will have two terms. It'll have the divergence in the vector calculus sense of b hat, which is this part. It's the original reverse drift plus the divergence of the A matrix. And the terminal cost is going to be negative log density at time zero, right? Because what's going to happen is when we reverse the time, its terminal density is going to be the initial density of the original forward process. So that's exactly the terminal cost. And here the idea is as follows. We're going to assume, just like Hausmann and Pardue assume, that the density of the forward process solves the Fokker-Planck or the forward Kolmogorov equation. And then we can simply write the density of the time reverse process, P bar, satisfying another partial differential equation. Simply just doing the differentiation, and then we write it like this. This PDE is equivalent to the Fokker-Planck equation for the forward process, but now we impose the terminal condition, right? Because the behavior of the reverse process at time capital T has to be the behavior of the original process at time zero, and we end up with the generator of the reference process given in the previous slide right here. So L hat is a generator of that reference process, and that only depends on B and A. And then we have this multiplicative term, right? So this actually equations like this is linear and can be solved using Feynman cuts. So now we know what the negative log density of the time reverse process looks like in terms of the reference process. So once we do it, this gives us the optimal control. The optimal control U star is exactly the score of the time reverse density, so gradient of the log. And the reason why we did it this way is, again, if you look at the case where the original forward time process has x dependence in B and in sigma, the additional term involves differentiating P acted on by the matrix A. So we need to separate that part out. And once we separate that part out, the control that we have to add is indeed A multiplying gradient log of the time reverse density. And so this holds for any non-random initial condition. And in order to obtain the full solution, we have to follow our strategy of dealing with constrained marginals. So we constrain a marginal to be px0, and that's exactly how we end up with this mixture of the Gibbs densities. Okay. All right, so this is the time reversal. And of course, it's an interesting setup precisely because time reversal is really a component of generative models based on diffusions. And so the main effort in this goes into learning the score term. So in these algorithms, a neural network is used to approximate this gradient log P based on sort of the paths of the forward equation. And so really what's happening is that we're solving an optimal control problem using a particular parameterization of the value functions, right? Because we know that this negative log P is actually the cost to go of a certain control problem where the costs are given in this way, right? Did I have that? Yes. This is the cost, right? We have the divergence of the time reverse drift, and then the terminal cost is the negative log target density. Okay, so that's that, and then I would like to discuss the related problem, which is the Schrödinger bridge problem. So Schrödinger bridge problem, in a sense, is kind of related to some of the questions that have been raised in the context of these diffusion models, right? If I have a process that has a particular stochastic behavior, how can I minimally perturb it in order to obtain some desired stochastic behavior, which is different, right? So that's precisely the idea. I'm given initial and target densities, P naught and P1, and I would like to find a minimum energy drift, U, which is just an adapted process that has finite energy, so finite integrated squared all 2 norm, such that when I add this drift to a given reference process, I steer its final density towards well, this should be right. Should be P. I didn't use P1. So P naught is the initial density. P is the desired final density. So if we don't use the control, our reference process started at P naught will end up with some density, let's say P tilde. But I add the drift in order to steer this density towards P, and this drift should be a minimum energy drift in the sense that it minimizes the integrated half squared all 2 norm of U. So this problem was really first posed by Schrödinger in 1930s, and he was interested in sort of this structure of the laws of physics. The idea was something like this: suppose I have a bunch of particles clustered at the origin, let's say, clustered at some point, and then they start moving around. And my hypothesis based on sort of physical intuition is that they're undergoing just straightforward diffusion, right? They're just diffusing following following the usual equations, the diffusion equation. So if this hypothesis is correct, if I were to record their positions at, let's say, t equals 1, I should end up with a Gaussian shaped histogram, right? Because the probability density of along the heat flow is just a Gaussian. And suppose I look at this histogram and it does not look Gaussian at all. It has modes that should not be there. It has a different shape. So that means I have to modify my original hypothesis. There have to be some forces present in order to steer these particles towards some behavior that is not consistent with the usual diffusion equation. So what's the minimal such assumption? Minimal in the sense of minimizing this total energy needed to be injected into the system. And we, of course, through the reformulation, for example, by Hans Filmer and Dai Pra, can view it in terms of a relative entropy constraint when we transport the dynamics of the reference equation to the one that gives us desired P. All right, so the reference process just has this form. We're given an initial density P naught. We have given drift B, given diffusion matrix sigma, and we assume that this process is regular enough to have time-dependent transition densities. So this QST of xy is the conditional density for the position of this process at time t. That's y, given that the position at time s was x. So we assume that these transition densities exist and are sufficiently well behaved. And the approach to solving this problem goes through essentially an analog of notion of coupling, but for processes. So what I want to do is I want to couple two measures through the transition function of a Markov process. And so the result due to Berling and Jameson basically says that if I give you P naught, which is the initial density, P, which is the desired final density, and Q, which is a given transition family of transition densities of a Markov process, then you can couple P naught to P through this process with transition matrix transition densities Q simply by means of just two sigma finite measures, nu naught and nu. And so nu naught and nu are solutions of a particular problem, such that this pi, which is now a measure on Rn cross Rn, has the right marginals, P naught and P, respectively. Right, so the idea is that I'm not allowed to have arbitrary couplings of P naught and P. I have to have the ones where the transition density Q is involved, right, from time 0 to time capital T. So assuming that this problem is solved, let's formulate a control formulation, a control interpretation of this. So I'm going to let P tilde be the density of the reference process at time capital T. So if I don't add any control, if I start with P0, I'm going to end up with P tilde at time capital T, right? And we're going to define mu tilde as basically the probability measure with this density. We're going to assume that mu, which is what is mu? Oh yeah, mu is the measure that the target measure, right? Assume that is going to be absolutely continuous with respect to mu tilde, right? So that's the kind of a big structural assumption, but it's not terribly restrictive. And then from that you can argue that nu, which is this measure in the Berling-Jameson representation, has a Lebesgue density, call it m. And you can see the argument for this in, let's say, the paper of Dai Pra. Then we're going to introduce the Gibbs measure. So the Gibbs measures involve, of course, the Hamiltonian. So we're going to look at the ratio of m, which is this density of nu. Remember, nu is the measure at corresponding to the time capital T situation through this Berling-Jameson decomposition. That's what accomplishes this constraint coupling. So what we're going to do is define define this Gibbs ratio, and you can actually show that in fact, if you integrate this with respect to x, you end up with 1. And so here, rho is essentially this precise density. So what we're doing here is we're taking q from lowercase t to capital T. That's the transition density of the original process started at time little t, and we're looking at the average of m at the terminal time. And that's why you can actually show that when t is equal to 0, we start at the initial time 0, we integrate this. And so we do end up indeed with a valid probability density. So we can introduce the following Hamiltonian. The Hamiltonian here is simply negative log m, right? So that means that there's no running cost. There's just this control problem has a terminal cost, right? So that means precisely that when we look at the optimal control formulation, thinking a little bit ahead, the control cost will only have the squared L2 norm of the drift, right? Because f in this case is 0. So that means that we have to expend the budget that we have in order to steer these particles along towards just achieving the right final density. And then we can actually show that rho xt is the expected value of m. I mean, that's exactly what we're doing here. And that's the reference process started at the intermediate point. Once again, we're think about the cost to go. All of these manipulations are fairly straightforward. They are just somewhat technical. And then the control U star is actually going to be gradient log of this rho. And then we can sample from the desired Gibbs measure for any non-random initial condition. And then, of course, the overall solution follows by constraining the marginal law to be P naught. And that means precisely that we're going to have a Gibbs mixture, right, with P naught determining the mixture density. So we can do a bit of a calculation, compute the free energy. So when I start my process at a non-random initial condition, that one is the easy case. The free energy is actually, that's precisely the control cost, the minimum control cost. This is precisely the energy that we use up when we introduce the drift in order to attain the desired density at time capital T. And this is the terminal cost. So we, of course, know that this is equal to negative log of this expression, right? Because that's precisely our e to the minus h kind of a situation. And that actually has the negative log density of mu naught with respect to nu naught. Remember that mu naught is the initial measure, right? So it's p naught x dx, and nu naught is the initial Berling-Jameson measure. That's what we end up with when we introduce this coupling of p naught and p through our transition density q. When we have the random p, of course, then we have to average the Gibbs density with respect to p naught. And when we compute the free energy, we actually end up with the negative relative entropy between mu naught, which is, again, the initial density, and nu naught, which is the initial Berling-Jameson density, right? That's the one that's determined through that coupling. So it's interesting that, in fact, the total cost just ends up being this relative entropy. And so the minimum control energy that we need to consume here, right? This is the first term, right? This is that question in the Schrödinger bridge problem. What's the minimum energy we need in order to steer the reference process towards a given terminal distribution? That is actually the difference between two relative entropies, right? We have the relative entropy of mu and mu tilde, and let's remember what those are. Mu is the desired probability measure. So it's that's px dx. And mu tilde is what you would have at time capital T if you did not apply any control. So mu tilde is the uncontrolled terminal density. And so that we have this relative entropy, and then we have the relative entropy between the initial measure and the initial nu naught, which is, again, what allows us to have this coupling through Q. And the difference of these two relative entropies is actually non-negative and is equal to just the control cost, right? The minimum control energy. And that's the result that Schrödinger kind of derived heuristically, and then Fulmer and Dipra showed rigorously. But it actually arises explicitly through a solution of an optimal control problem. In fact, we can do a very simple calculation for the simple case when the initial distribution mu naught is just a Dirac at zero. So we start with the deterministic initial condition at zero, and the desired Gibbs density then looks like this. So suppose that our B is zero, right? So there's no drift. We want to perturb the Brownian motion, right? So if I start a standard Brownian motion starts at zero, at time capital T, I'm going to have a Gaussian whose covariance is proportional to capital T. Suppose I want to perturb it, steer it towards a desired density P. So then my Gibbs density that I want is actually just the likelihood ratio between the target P and the Gaussian gamma T. And the optimal control in this case is this is a very simple calculation. It's given by gradient log of the expected value of the target density evaluated at where the standard Brownian motion will be at time capital T minus little t. And the minimum free energy is zero in this case because we want to achieve. So here the idea is that if you look at this kind of a thing, this is going to be the relative entropy between P and gamma T, and this is going to be this is going to be equal to this is going to be this is going to be the minimum free energy, and that one is zero. And so we end up with the fact that the total energy needed by the control, right? You use all of it to bring the density of your process at time capital T to the target, to P. So perturb. So that means that the controls become more and more singular as you approach the time capital T, because the variance actually has to decrease. It has to be proportional to capital T minus little t. So as you approach capital T, the drift becomes more and more singular. You essentially end up with something like a generalized Brownian bridge. So the interesting thing is that this is actually a special case of a more general setting where you have to solve this forward-backward problem in order to determine nu naught and nu one. And finally, I'll just close with I think close to an hour. The original result of Mitter and Newton, they were interested in this kind of non-causal filtering, where you have a diffusion process X, you observe it with white additive Gaussian noise, and given this entire path YT, you want to have a probability density of XT. And it turns out, just as they showed, this was the original contribution, that you can sample from this posterior of x little t given the entire observation path using essentially just a drift added to the original process. So simply just to summarize, the sampling of diffusion processes using optimal control ideas actually allows us to think about as I said, sampling is an optimal control problem. So even though you're asked to sample from a Gibbs density, all you're doing is adding a drift, which is obtained by solving an optimal control problem. And of course, Mitter and Newton was really the first work that phrased it in the context of non-causal filtering, but actually extends to other settings, including these Feynman-Kautz average computations, time reversal of diffusion processes, and time reversal for these generative models and the Schrödinger bridge. And I think that's all. And as I said, the full paper is on arXiv, but it'll appear in Communications and Optimization Theory pretty soon. Thanks a lot.
Thank you very much, Max. Any questions from the audience? Feel free to unmute yourself and ask. And if you're feeling shy, you can put it on chat, though. And I'll ask Max.
So, hi, Max. Nice to see you.
Hey, Venkat.
So,
It's been a long time.
yeah, it's been a long time. Yeah, I hope to see you in person sooner. In the interest of asking something kind of provocative, so
Yeah.
assuming that one is interested eventually in the application of trying to generate some distribution, what is the rationale for focusing only on diffusions?
Uh, right. So the idea was to implement the sampling process as a composition of relatively simple steps. Right. And so some of the genesis of these diffusion models in machine learning kind of goes back to some work bridging deep learning and hierarchical Bayesian modeling. So the idea was that if you want to sample from a complicated multi-dimensional distribution, what you do is you have a time inhomogeneous Markov chain where at each time t you sample from a Gaussian whose mean and covariance are some neural network parameterized functions of the previous iterate. Uh, and so this allows you to for example fit parameters to data using gradient descent. You can just backpropagate through this using basically Stein's lemma. So it's kind of a marriage of ideas from MCMC and uh, gradient descent with backpropagation. So once that model was in place, this kind of paradigm of building up complicated distributions by iterating these simple steps, right? All you need to do is just compute the current mean, current covariance, and then sample from a Gaussian with that mean and covariance. Assuming that step is available to you, then you can implement more complicated processes. So the one of the first, right? So that was really the rationale for using diffusions. But one doesn't have to use diffusion processes. I think these days you can actually accomplish similar things with let's say Markov processes with more general state spaces. For example, finite state spaces, you can use jumps, although I haven't seen much work in that. But I mean, like I said, the original rationale is that you want a certain computational tractability.
So I guess I should explain where I'm coming from. I mean,
Yeah.
the rationale you offer is a historical rationale, but the last two examples you gave are quite related, of course, right? The
Yeah.
Schrödinger bridge is just
Yes.
a version
Yes.
of time
Yes.
reversal and generative diffusions.
That's
So
exactly. Yeah.
if you pose the problem, so to speak, from first principles, what you want to do is to arrive at some distribution P1,
Right.
starting from some easy to generate distribution P0.
Exactly.
And
Yes.
you have some cost associated to the transit, but there's no
Right.
reason to restrict yourself to diffusion. So
Absolutely.
yeah, so and you
Yeah.
might still end up getting a solution that you could implement through some learning process by
Right. Right. Right.
yeah, right. So is I
Yeah.
guess presumably that is something people are thinking about then, yeah.
I think so. I
Okay.
think so. Yes.
Okay, thank you.
Sardar, um, you seem to be on video, so I presume
Well,
that's to ask a
I just want to
question.
say hi to you, Max. But now that you asked
Hi,
me,
Sardar. Yes.
what I find fascinating about this approach is that Max, what you do is that you add control, and then with the control, you think of the set of all attainable path valued measures,
Yes.
which matches something else. And in a sense,
That's
this
right.
says that if this control is my answer, what is my question? And you're able to obtain a variational interpretation of that matching problem. And I think this is a
Right.
very beautiful argument.
I think right, and thanks. And I think actually another interesting point here is that this actually tells you not just the behavior of, let's say, initial and terminal densities, but even in the case of time reversal, it tells you that the entire path density for a time reverse process is characterized. And the characterization is a Gibbs measure where the potential is actually the cost to go. And so here, I mean, there have been approaches to optimal control using entropy methods. So, George Savigis had some papers and I think a book on this. I think in the book he tried to argue, for too much. He tried to argue that this should be the foundation for all kind of intelligent control systems. But in a narrow setting, I think kind of viewing control problems as measure generation problems, right? And this was Benish's innovation. He actually basically more or less said this. Let's go with the weak notion of solution, and that way a control problem is simply just well simply um, you know computing a functional integral in over a Wiener measure with an importance weight attached to it. I think if we go with that, that actually does give us an interesting structural understanding for the paths of diffusion processes under different different structural constraints. So yeah, I think that's a very interesting sort of direction. It could in fact go along with Venkat's question that we can we can consider a broader notion of a path in a space of measures without necessarily being realized as a diffusion process. In fact, this is actually something that I'm working on with one of my new grad students. In fact, he did his undergrad at McGill and did some independent study with Peter Keynes. So we're thinking about formulating the notion of controlled dynamical systems in the space of measures intrinsically. And then you can ask your question of what's the best realization of this flow of measures in terms of a process. And it could turn out the diffusion process realization is in some sense preferred because the continuity, let's say, of the flow as a function of time in the space of measures translates into, let's say, sample path continuity. But you don't have to hold to that. You can relax that.
So, Max, very nice presentation. I wanted to ask you a question on this, maybe slightly unrelated to the presentation, but it seems to me that much of the discussion is on measures over Euclidean spaces.
Yeah.
Do you have any comments on how we can extend it to infinite dimensional spaces? If we were to sample, if we wanted to sample from an infinite dimensional space, is it possible to extend, like I know you just mentioned about the fact that you can reformulate the problem in the space of measures and in the space of movement of measures, controlled measure process. So can we do something like that for the infinite dimensional?
I mean, it should be possible, right? There's, for example, there's a book by Da Prato and Zapchik on essentially stochastic differential equations in infinite dimensions. So you can transfer a whole lot of the theory into SPDEs, let's say, if you just have a way of defining Gaussian measures on a Banach space. So I think just the technical sort of difficulties are most, like I said, mostly technical. I don't think they're substantive in the sense that the kind of the conceptual underpinning would change by a whole lot. Because for example, you can think about random fields. Right. I mean, Vollmer actually had a survey called Random Fields and Diffusion Processes, where the first part is this kind of a De Bruijn formula, De Bruijn-Lanford-Ruel formalism, if we're talking about random fields, and the second part is now suppose I have a random field, but the sites on that random corresponding to that random field are actually spaces on which diffusion processes are defined. So you have kind of an local interaction between diffusion processes. So you actually do have an infinite dimensional object. And for that, and then you can talk about sort of, the Schrödinger bridge-like problems, but then you kind of combine it with this, DLR local specification type ideas. I think one can do some interesting things for sure.
Yeah, I think there would be applications of that in the context of condensed matter physics from the point of view of new material discovery. So that's where the motivation comes from for studying.
Yeah. No, that's a great question. Yeah.
I'll ask one, and this is kind of maybe slightly orthogonal to some of the things that you were talking about, Max. But is there a version of this for not just like one source measure and one target measure?
Like
let's say a family of exactly, a family of sources and a family of targets. I mean, how would one even start?
Oh, you start from a family. Oh, I see. Okay, so this is actually kind of either a version of something like ensemble control, right? When you have initial measures parameterize some parameter theta, and you want a single control that would transfer like mu naught of theta to like mu one of theta for each theta. Yeah, I haven't thought about it, but yeah, I mean, I think one could probably set something up, along these lines.
Because this is like, in statistics, this would be like a change of experiments problem, right? This is
Yes,
essentially the sort of the original Blackwell formalism, but now through
that's
the
right. Yes,
perspective of optimal control.
right. True. So, that's a good angle.
All right, we are 10 minutes over the scheduled time.
Apologies.
No worries at all. And this is not to blame you at all, Max. But this is where the video will end. So if anyone wants to hop on